So this is going to be the last video in which I'm talking about the stability of different element pairs. I've seen a couple of examples. We've seen three different element types with three different types of behavior. We had one element that showed locking, one element that showed spurious modes, zero energy modes, pressure oscillations, and then we had one element that was stable, and we didn't quite understand yet why this element was stable. Now we had a bit of a rule of thumb to get an idea of the performance of elements. It was this degree of freedom counting strategy where we have a constraint ratio, and if this constraint ratio was very low, then we had severe chance of locking behavior. When it hits the limit that we expect, the true ratio between constraint equations and degrees of freedom, then we expect to get good results in terms of the constraints, so we get divergence-free solutions or good divergence-free approximations. But we saw that that might still mean that we have certain oscillations in our pressure field, and actually only for the larger values of this constraint ratio we got stable results. So we're trying to move away from this rule of thumb idea a little bit in this lecture and go towards something that is a stronger requirement, a more tangible result. And we're going to try and discretely determine what our Inf-sup constants are. Now, I've said before that these constants actually depend heavily on the choice of finite element, the choice of mesh, the boundary conditions, and that's why they're so difficult, right? That's what made them so different from the coercivity constant. And so we're gonna try and do this in a smart way such that we can try and draw some conclusions about an element in general based on a series of results of different gamma values for different successive meshes, for instance. So here we have our Inf-sup statement again, infimum over the pressure field, the supremum over the velocity field, and then we have our bilinear form divided by these norms. Now, the true Inf-sup value is defined to be gamma, and we want this to be larger than 0. And if this is larger than 0, and we also satisfy our other LBB condition, then we actually get a solution. We have a uniquely defined solution for which we know that it will exist. Now, something that I haven't really talked about yet, but that is really just as important, is also convergence of this solution. So now we know that the solution exists. Does it also converge? Well, and in a very similar way as that the coercivity constant also had to do both with the existence of the solution, but also gave us an idea about the convergence of our finite element approximation. In much the same way, also this gamma constant shows up in the convergence characteristics of our method. And that's what I have on the second line here. And actually the statement that you would get if you would work out the mathematics is that you have a bound on the H1 norm of our velocity plus the L2 norm of our pressure. And that's going to be bound from above by some constant c times the mesh size to the power of, well, the minimum between our polynomial order of velocity and the polynomial order of our pressure plus 1. And so this already kind of illustrates that you get sort of optimal behavior if your space of velocities is one order higher than your space of pressures, because then that minimum is attained for both PU and PP plus 1, that's the same value at that point, so we're not wasting any degrees of freedom in a sense. And our Inf-sup constant shows up in the C in front of this H. That's our constant of proportionality. We've seen this before also for the advection diffusion equation, and for the advection diffusion equation we saw that based on the coercivity constant, this constant C here shifts up or down in our arrow graphs. And in a very similar way, we now have also an inverse proportionality with respect to the gamma value. Meaning that if we have a large gamma value, then C is small, which gives us a tight bound on our error. Whereas if we have a very small gamma value, so a value that tends towards this 0 here, then we get, we can almost not say anything about our error. It just says that it's going to be smaller than something that is very large. Well, that's not very useful. Yeah, so the Inf-sup constant has two important functions in our analysis. Firstly, it says something about the existence of the solution, and then secondly, it deals also with the convergence of our finite element scheme. Okay, so let's try and put this into perspective based on what we've seen so far on the different elements. And I'll draw them again. We have three of them. We had the P1, P0 element. Those were triangular elements where we have first order basis functions for our velocities, and we had constants on each triangle for our pressures. Then we had the Q1, Q0 element, which was a square element. And again, we have linears for our velocity field and a constant for our pressure field. And then lastly, we had the P2, P1 element, which again was triangles, where in this case we have quadratic basis functions for our velocity. We now have a continuous field of linear basis functions for our pressures. Now, these are the elements that we analyzed in previous videos, and the things that we observed were that our P1, P0 element showed locking behavior. Our Q1, Q0 element had spurious pressure modes. And our P2, P1 element, which we called the Taylor-Hood element, was a stable element. And we also calculated, Taylor-Hood. We also calculated the constraint ratios corresponding to each one of these elements. We had, we saw locking, meaning that the constraint ratio was too low, and indeed we had R is equal to 1 here, whereas in 2D we expect the value of 2. For the Q1, Q0 element, we had that optimal value, R is equal to 2. And for our stable element, we actually had a value that was too high. R is equal to 8, which meant that in terms of the incompressibility, our solution didn't quite satisfy that constraint very well. But nevertheless, it was stable. Now, what else did we observe? Well, since this is a locking element, and let's talk about this convergence now, we always have the same solution if we use this element, namely a solution where we have a zero velocity, a completely locked system, right? So in that sense, we have absolutely no convergence here. And in terms of convergence, can we actually say anything about an element that has this spurious pressure modes? Well, we saw that we had a velocity, but our pressure was really, it's not even defined, right? We have this arbitrary solution in our pressure that we can add or subtract, and it's not going to make any difference in our matrix systems of equations. We do not have a unique pressure solution. That's what these spurious pressure modes mean. So there's really not much use talking about a convergence here. In fact, we have an undefined solution. Undefined. And the Taylor-Hood element is actually one that has optimal convergence, and that is also due to this this condition here where we have this minimum between Pu and Pp plus 1. Well, Pp is 1, Pu is 2, so we actually have h to the power of 2. Yeah, we're not wasting any degrees of freedom in our pressure or our velocity. So we get an optimal convergence here. Okay, so based on these observations, what can we say about the Inf-sup constants that we apparently have for each one of these elements? Well, the center one is the easiest one to think about. We have an undefined pressure solution. Yeah, we know that corresponded to our B part of our matrix being not full rank. and not being full rank meant that the Inf-sup condition was not satisfied. Specifically, we have a certain pressure field such that if we substitute that in place of Q here, that we get a zero value for that integral, right? That's precisely what we showed, that we have a certain pattern in our pressure such that this integral yields zero. Now clearly, if this integral yields zero, then the infimum is not going to satisfy this, and in fact the Inf-sup constant that we get for an element like this, so our gamma value is going to be zero. Yeah, so this was the element where we have an Inf-sup constant gamma is equal to zero. So is the Inf-sup constant of either one of these other elements zero? Well, clearly for the stable element not, right? But how about for this locking element? That might actually be a bit of a tricky question, because it might seem like the obvious answer is yes, but in fact it's not. We have a well-defined, a non-zero Inf-sup constant for elements like these. And that is illustrated by the fact that we do get a solution. Even though it's not a very good solution, and it's a non-convergent solution, we do get a unique solution, which means that our B matrix had to be full rank, which means that the Inf-sup condition is satisfied, which means that we get a gamma that is larger than zero. So based on these observations, we can conclude that even though it's not a very good element to use, we do get a gamma value of larger than zero. Now, is there something else that we can say about this? And maybe I can actually come back to that after we've also talked about the Taylor-Hood element here. So we get an optimal convergence. So we have a solution, again, gamma is larger than zero. But if we now compare the left and the right element, and we have a look at our convergence criteria here, then we can make another observation in regards to the gamma parameter. What this statement says is that the error is going to be smaller than or equal to c times h to the power of some exponent, right? If we have no convergence, then the only way that that's going to happen if this is proportional to a constant. If that is not going to decrease with h. Because if this statement here decreases with h, then we will always get some convergence of our error. Now I have an h right here, so how is it possible that this would not depend on h? Well, clearly that means that the gamma value has to also be proportional to h, but now because we're dividing by gamma, this would mean that gamma would also be proportional to h in pu comma pp plus 1. Right? So if we have a larger than zero Inf-sup constant, but this Inf-sup constant actually scales with the mesh size, then we still don't get any convergence. And that's precisely what we have for this left element where we have locking. So even though it's larger than zero, it's actually going to be of the order of, well, h in this case. The order of h min pu pp plus 1, that is h to the power of 1 is h. Yeah, so let me get rid of this. Yeah, so now we can actually make a conclusion about our Inf-sup constant for this element, and we'll verify this later. We'll get back to this. So now we have a 0 here. We have a gamma that is of the order of h over here. And how about the one on the right? Well, this one had optimal convergence, which means that c is actually independent of h, and that means here that our gamma value is also independent of h. So gamma is going to be of order 1, yeah, constant. Okay, so this is what we expect from our Inf-sup relations for these element choices. How do we go about verifying that? Well, what we're going to do is we're going to devise a strategy for discretely determining our Inf-sup constants. And again, we're not able to do this in general. We're not able to do this for any arbitrary choice of mesh. So what we're going to do is we're going to do this for a successive set of meshes, and we're going to draw conclusions on the dependence on h, whether it's positive or 0, and whether it remains constant along these mesh refinements. Now that's not going to give us any guarantees for any choice of mesh and any choice of boundary conditions, but it's just about the best we can do. Okay, so that's our objective here. How do we go about doing this? Well, there's always two sides to talking about discrete methods like the finite element method. We can talk about them in terms of functions in discrete function spaces, or we can talk about them from the linear algebra perspective. And these two perspectives are going to be equivalent, but either one is always going to be the more natural way of looking at things. And I think for what I want to talk about today, the most natural way to look at things is from the linear algebra perspective. So what I'm going to do is I'm going to replace all these L2 norms, H1 norms, and these integrals by discrete multiplications of vectors and matrices. That's precisely what we do if we construct a finite element stiffness matrix. Okay, so I need to be able to represent three quantities as matrix multiplications. Those are this one and each one of the L2, each one of the norms. Okay, so how do we go about doing this? Well, hopefully this is a procedure that you're familiar with, or at least are able to follow quite straightforwardly. And the first thing what we're going to do is we're going to rewrite our finite dimensional, a discrete function as a sum of coefficients times weighting functions, right? So given a function QH, discrete in our discrete space of pressure functions, as the sum over I is equal to 1 to nq, so we have nq number of basis functions and number of degrees of freedom for our pressure field, of basis functions nx times weighting coefficients q hat I is what I'm writing here. Yeah, so this is a sum, or summing over the same index, so we can also write this simply as a vector transpose times a vector. This vector I'll call nt. So this is now a vector of shape functions evaluated at a point x and multiplied by a vector of coefficient values. I think I've been implicitly going back and forth between the notation on the left here, where this is really a function of x, and the notation all the way on the right, which is still a function of x. We haven't changed anything, right? These are all equalities, but this gives a matrix interpretation to our equations. And similarly, we have such a representation also for our velocity as a sum from I is equal to 1 to the number of degrees of freedom for our velocity space of, well, again, basis functions, but these might be different basis functions. I'm going to write these as with the arrow on top because these will be vector valued basis functions. But other than that, I'll just stick with the same letter. Ni times, and now again weighted by the coefficients v. And we can again write this as a vector of these vector valued shape functions transpose evaluated at x. This becomes now the vector times the coefficient of weighting values. Sorry, there should of course not be an I anymore here. There we go. Okay, so this is an identity, right? We can write any discrete function in this way. So given this representation of these discrete functions, what can we say about our integral of QH div V H? Well, we can substitute these different relations and we would actually obtain a nice matrix system of equations. Let me actually write this as an identity. This is going to be equal to Q hat transpose, so this vector of coefficients here on the right, multiplied by a matrix B times V, where B ij is defined as, well, the integral of our nx I times div of nj. Yeah, our shape functions are are basis functions for pressure and velocity. And that is, of course, exactly the B matrix that we've been talking about all the time when we talk about our Stokes equation as being A, B, B transpose, yeah? And 0. Yeah, so that's how we obtain that matrix. Now I'm going in a little bit more detail than I tend to, just because I want to make sure that the steps are clear. So in the same way, we also want to be able to write the norm of a function QH. Well, QH was a function in L2, so that's going to be the L2 norm. And remember that the L2 norm was exactly defined as the L2 inner product of QH with itself, and then the square root thereof. So in very much the same way as what we just did above here, we can write this L2 inner product as a matrix multiplication of well, two functions that are both Q. So this is going to be equal to Q transpose hat times the mass matrix is what this is. And let me also write the subscript Q here, times Q, and well then again the square root, where MQ Ij is defined as the integral of, well, just the two shape functions of Q. Now, sorry, J, I. Yeah, we can do the same thing for our H1 norm. Which we can also write as a multiplication by a mass matrix. And now actually this mass matrix is defined a little differently. Because of course we know that the H1 inner product was a combination between the L2 inner product of the function and the L2 inner product of the derivatives of the function. So actually this mass matrix Ij is going to be defined as the integral of well, the two vector basis functions from V. Why do I do that? Ix, well, a vector dotted with a vector basis function J. But additionally, we have also the gradient of these two vector basis functions, which have to be double contracted. Yeah, so for each I and j, we have a fixed basis, so we can simply compute the values corresponding to each one of these integrals, and if we do that, then we obtain the mass matrix corresponding to the H1 norm. So typically when we talk about the mass matrix, then we think of something along these lines, but in fact that's really just the L2 mass matrix. Every different function space has a different mass matrix. The mass matrix is just a matrix that gives you the L2, or sorry, the corresponding inner product if you perform this operation. Yeah, so for different function spaces, L2, H1, H2, you actually have different mass matrices. Okay, so now I have discrete representations of each one of the integrals that I wanted. These ones were precisely the ones I needed for my Inf-sup condition. So with those representations, let's rewrite the Inf-sup condition, but now not as functions in a function space, rather than that as coefficient vectors in simply spaces of Rn, so vectors of coefficients. And what we would get if we would do that is that we have the infimum of, well, over all our pressure functions, which are now encoded by Q hats in a set of R to the power n Q, right? That was what we had here. And then we take the supremum over all our velocity vectors of coefficients in R and V. Then we have our B matrix. So we have this integral, which we write like this. So we get Q hat transpose B V hat divided by, well, the L2 norm of our Q function, which we write in a discrete sense as Qt mq Q hat, and then the square root thereof, and similarly V hat T mv V hat. Okay, and we're hoping to find, now this defines a gamma, and we're hoping to find that gamma is larger than 0, so we require, for a good finite element method, we require, well, first of all, gamma is larger than 0, that's going to give us a solution, a unique solution, but also gamma independent of h, and a value that's not going to change if we refine. Okay, now does this make things any easier? Well, now we can start playing around with matrix vector multiplications and try to simplify this. So remember, the way that we handled our Inf-sup conditions was from the outside inwards, meaning that we fix a certain Q, and after that we're going to take the supremum of whatever this operation might give us. That's going to just be a value, so we're going to take the supremum of all values for any choice of V. After we've done that, we're going to change our Q, and we're going to do the operation again. And like this, we're going to loop over all possible Qs. And then the final value gamma is going to be the minimal value after we've considered all possible choices of Q. So that means that for a given Q, I can substitute a relation, I can substitute something for V. That's what we did before as well. We did one example, if I'm not mistaken, one example of Inf-sup proof for the pure advection equation, where we wrote the one field in terms of the other. Also in the homework assignment, I have one example where you have to prove Inf-sup, where again you have to write one field in terms of the other. And it's always from the inside. We're going to write the inner function V in this case in terms of the outer function Q. So I want to write V in terms of Q, and naturally I want to do this in a smart way, in such a way that I get something that has a large value. Now, you can play around quite a bit. Most of the time it's not going to work out, right? If you write V is equal to a vector of ones, then you won't get a constant. But for some smart choices, we do end up with good results. And since we're taking the supremum, we're happy with any result that we can get. So I've played around with this for quite a while, and this is the choice that we're going to use. So let me write this differently. Choose. We're going to choose V hat is equal to the mass matrix of the V space inverse times B T Q hat. Now the inverse of the mass matrix always exists. So why did I make this choice? Well, if I'm making this choice, then my equation that I'm trying to solve actually simplifies quite a bit. I get all kinds of symmetries in my equation, and actually some parts even cancel, right? So I played around just until the point that I found a relation between V and Q that gave me such properties. So what do we get if I substitute V hat like this in the above relation? Well, first of all, after that, I don't have a supremum over V anymore. I picked a certain V, right? So we only have the infimum over Q. So we have the infimum of Q hat in R and Q of, and now this expression becomes quite lengthy. Let me start off by writing whatever is under the fraction here. So we have still qt m q q and the square root. And the second one is now going to be v mv, where we replace v by this. So first we get v transpose, so that gives me q hat transpose b mv minus 1 transpose. Well, since the mass matrix is also symmetric, this is still simply minus 1. So now we're multiplying this by mv, and then we're multiplying that by v. So we get mv, and then multiplying that by v. So that again gives me m minus 1 v bt q hat. And all of that under the square root. How much above here? We have a qtb, that's the one we already had. Then we had a v here, and again we've replaced that by mv minus 1 bt q. Now, clearly mv inverse times mv is going to be identity. Yeah, so essentially those two cancel, and after we cancel those two, we see that precisely what's in the square root here, whatever is left, is precisely what is over here. Yeah, so this is essentially, the upper part is essentially the square of this part, and I can divide by those, and I simply get a square left over. Now let me write that as well, and actually let me make one small change here. I now know that whatever gamma I had here, it's going to be larger than or equal to this, right? Because we're taking here, gamma is defined to be the supremum over all choices of v, and I'm making one particular choice of v. I'm not sure if that gives me precisely the supremum, but at the least it will give me some value, and gamma is going to be at least smaller, or at least larger than or equal to that. Okay, so then let me now continue with what I was just saying. So I'm dividing by whatever is in the square root here. So now I have the infimum over q hat in r and q of the square root of qt b mv minus 1 bt q divided by q hat t mq q hat. Okay, now that's a much nicer expression to work with, and particularly because we have not only significantly shortened our expression and only have a dependency on q, but also because these matrices are relatively well defined. On the bottom we have mq, we know that's a symmetric positive definite matrix, and that's by virtue of it being a mass matrix. Now on the top here we have B, which we know very little about. We don't really know if it's full rank or not. We don't know if it's definite or positive definite. Most likely not, because it's not going to be symmetric. But if we multiply B by MV inverse and by B transpose, then the result is always going to be a symmetric matrix. So on the top we have the symmetric matrix, and on the bottom we have a symmetric positive definite matrix. So we write that down. We have two properties now. B mv minus 1 times B transpose is symmetric. Well, let me also write down, this is a matrix in the space R n Q, right? Q rows and R n Q. Yeah, because I have to pre and post multiply it by Q, is symmetric. And also NQ is also a matrix in that space. R and Q cross NQ is symmetric, positive, definite. So given that we have a symmetric matrix and a symmetric positive definite matrix, we can make the following statement. If I multiply the first matrix, B mv minus 1 bt, by any vector q, then the result is going to be larger than or equal to lambda min of mq multiplied by that same vector, where lambda min is the smallest eigenvalue of the eigenvalue problem B mv minus 1 bt times an eigenvector is equal to lambda times mq times that eigenvector. Yeah, and I encourage you to think about why that is precisely yourself, but the key idea here is that due to the symmetry of these matrices, all of the eigenvectors are going to be linearly independent and are going to be orthonormal. Actually, that's the important property. They're going to be orthonormal, which means that you can write any vector q as a linear combination of these orthonormal vectors, and then you can write out this equation as the sum over each one of these multiplications, and then that's going to naturally be larger than or equal to the smallest case of this equality. And I think this is actually an argument that I make more often in my classes, also in the other classes that I teach, so I feel like it's probably worthwhile to try and understand the details of this. Okay, so now that I can make this claim due to these properties, I can replace simply what is above here by this guy, because we're taking the infimum here. And if we do that, then we obtain that that is going to be larger than or equal to, right? That's the larger than or equal to sign from here. That's going to be larger than or equal to lambda min of now q transpose, yeah, there we go, times what I've replaced this with, divided by the square root of q hat tmq. Square root, right? That's what we had. So naturally these two cancel, and that's going to be equal to the square root of my lambda min. Yeah, so to summarize here, gamma is going to be larger than or equal to lambda min square root of this eigenvalue problem. Okay, so the way that we obtain a discrete, the way that we can compute a discrete lower bound for our Inf-sup constant is by solving that eigenvalue problem. Now let's think about this eigenvalue problem for a second. So first of all, that's going to be pretty expensive. The sizes of these matrices are going to be of the order of the size of our number of degrees of freedom for our pressure space. So that's equal to the degrees of freedom for our pressure. And they're not going to be very sparse, I believe. I'd have to look into the details there, but this B times M inverse, I feel like M inverse is not going to be sparse. So probably you're going to have to deal with dense matrices here. So using this test to try and find out if your CFD analysis of tens of millions of degrees of freedom has a good Inf-sup constant is not going to be feasible. Yeah? So what we're going to do instead is we're going to try and solve this eigenvalue problem on a successive set of very, very coarse meshes to get an idea of how these elements behave. So for instance, what I'll do, and I'll show you the results in a second, is I'll take a 2x2 mesh, and then a 4x4 mesh, and an 8x8 mesh, and a 16x16 mesh, and I'm going to see how this eigenvalue changes with this mesh refinement. Now again, this gives me no guarantee that I will always get a good constant for any mesh, but the opposite is certainly true. If I don't get a good result for those refinement levels, then I will certainly not get a good result for more complex meshes. Now the second thing that I want to point out here is that we knew already from our previous videos that the Inf-sup relation had to do with the full rankedness of B. So how does that show up here? Well, this multiplication of B, M inverse B, if B is full rank, then that's going to give me a full rank resulting matrix. And a full rank resulting matrix will have only non-zero eigenvalues. The opposite is also true. If B is not full rank, then this multiplication of B, M inverse B, is also not going to be full rank, which means that it will have a zero eigenvalue. So that already gives us a direct feel for if we're going to have spurious pressure modes. If we have a zero gamma according to this eigenvalue problem, then indeed we have a non-full rank matrix B and hence spurious pressure modes. And other than that, we're interested in seeing whether or not this gamma is going to decrease with mesh size to test these requirements right here. The ones that we have at the bottom here. Okay, so let me show you the results. No, seems like I closed my PowerPoint. I have to move some windows around. No. There we go. Okay. So again, for the last time now, let's consider our problem of lid-driven cavity, where we have a square, where we know now our solution, right? We've seen this a couple of times. And we've also seen that for different choices of elements, we get these different types of behavior. And the elements that we're considering right now are the leftmost one, that's the Taylor-Hood element, and the rightmost one, that's the element that logs. And then the two in the middle are two examples of pressure oscillations, pressure modes. And we considered this one, for which we could actually show that the pressure mode was this checkerboard pattern, and that's what we're seeing here. But this one actually also shows the pressure modes. So for each one of these elements, I've performed the eigenvalue computation from our notes, and these are the results that we obtain. So this confirms pretty much exactly what we hoped to get. For our locking element, which is P1, P0, we get an eigenvalue that decreases at the rate of h. You can see here you have 0.45, 0.225, 0.1.5, something like this, I don't know. So you see every iteration of refinement, it divides by 2. And that's exactly what we anticipated here. We get something of the order of h. So if I refine my mesh by a factor of 2, then I get half of the gamma. So for our stable element, or Taylor-Hood element at the top here, we get an estimate that is constant with mesh refinement. And that's precisely what we want. Something that does not depend on h and is larger than 0. Then for our elements that has these pressure oscillations, the P1 element, we get 0 eigenvalues. And we have an Inf-sup constant of 0. There's a mode that does not carry energy. And that's the 0 eigenvalues here, and the 0 gamma, the 0 discrete Inf-sup constant. So the last one that is interesting, and that's kind of an outlier here, is our Q1, Q0 element. That's the one that also has the purest pressure mode. So it should actually be also on the bottom here. It should also have just simply 0 values. The reason why it does not is because it required we need to have the boundary conditions in there as well. So the way that I actually computed these eigenvalues is by assembling all these matrices that we just saw in the notes. And our purest pressure modes, the ones that we computed in the previous video, or one of the previous videos, it assumed that we could sum over all our elements by only considering the nodes in the center. That's what you're seeing at the bottom left here, and here as well. So that means that we had thrown away all the nodes on the boundary. And we can do that if we have Dirichlet conditions all across our square, which is the case for the problem that we're solving for here. Right? We have Dirichlet conditions all across the boundary, and that's why we're indeed seeing that checkerboard pattern. However, the way that I obtained my eigenvalue problem, I just took a collection of elements without applying any boundary conditions, and that's why apparently this one in that condition logs. So effectively, that would be the case where you have full Neumann boundary conditions instead of full Dirichlet conditions. But luckily, nevertheless, we still draw the conclusion that this is not a good element. I anticipate that if you would change the systems of equations, the matrices, to incorporate also the Dirichlet boundary conditions, then the Q1, Q0 element should also give 0 eigenvalues. Okay, now I think that's most of what I wanted to talk about in this video. That gives a bit of a more tangible handle to determining whether elements are good or not. Nevertheless, I think that the degree of freedom counting is very important. It gives you an engineering feel of what's going on. And this then gives you the more mathematical and numerical tool to verify that what you think is okay is indeed okay. Now, one of the main messages to take away from the last few videos is that this is difficult. It's difficult to find elements that have good performance, independent of the choice of boundary conditions, independent of the mesh size, independent of the number of degrees of freedom, or the mesh size in the sense of refinement, for instance. So having a very good element is always our best option. If you can prove this, then that's typically what you want to do. But at the same time, we kind of don't want to rely on this either. And that kind of moves us to our future videos. The next topic that we're going to address is what if for some reason we really do want to use the P1P element, because, for instance, I don't know, we have only implemented linear basis functions, or I'm not able to use discontinuous basis functions, or I don't know, for whatever other reason I want to use P1P1. Well, then the alternative is to stabilize, right? So just like we had stabilized methods for the advective field, we also have stabilized methods to handle this pressure oscillations. So then we go to pressure stabilization. And in the next video, I'll also give a few more arguments for why we might do that, but then you already have a feel of what we're heading towards here. Okay, so that's it for this video. Thank you for your attention, and see you in the next video.